All right, I wanted to do a short video going through the derivation of the electromagnetic wave equation, so I can skip that in class. So we're going to start talking about the electromagnetic effects in vacuum, basically. So in the absence of charges and currents, you can still have wave propagation. This will be light waves and radio waves. Now, as I was saying in class, to generate a light wave or radio wave, you need to have moving charges. That's what makes it start. But then the wave will propagate on its own away from the source, which was moving charges and changing currents. In that region, away from the charges and currents, we can write Maxwell's equations down in the following way. So I'll use the differential form. The divergence of E is proportional to the charges that are present. So if I'm in a region with no charge, that's 0. Divergence of B, as far as we know, is always equal to 0. There are no, as we say, magnetic monopoles. Now, the Faraday's law will stay the same with or without charges present. That's just going to be telling us that electric fields are generated by time-changing magnetic fields. And then I have an equivalent Ampere's law, curl B, and that's going to be due to time-changing magnetic fields, or sorry, electric fields. So I have mu naught epsilon naught times dE dt. Okay, there are our equations. So it turns out I can combine these into an equation for a single field by just taking the curl. So if I of one equation. So if I take this equation and take its curl, so I have curl E, okay, equals minus, and here's what I'll do. I'll take the curl inside the time derivative. Okay, you see that now I can use this equation here to replace this, and that's going to give me that the curl E is then going to be minus epsilon naught mu naught d squared E dt squared. Okay. All right, so I want to reduce this down a little bit more. I can use a vector identity here. It turns out, and this I will not prove to you here, but it turns out that if you take the curl twice of a vector, okay, so say some vector v, then you can rewrite this as the gradient of the divergence of that vector, okay, minus the what's called the Laplacian of the vector v. Okay, so the Laplacian is really just, let me write it on the next page. Okay, so I'll come back to this expression. The Laplacian is really just defined as the divergence of the gradient of a vector. Okay, this becomes, so it's a second derivative. And really, the Laplacian is in Cartesian coordinates is quite simple. Based on this expression, it's just the second derivative of each in each direction. Okay, this is what I mean by Laplacian. Okay. All right, so now I need to go back and just point at what I had on the previous page, and I'll move on from there. So if I now look at the bottom here, so what I can do is replace the curl of E, or the curl of E, sorry, here, with this expression. And it turns out, so because we're in a region when there are no charges, this part will be 0, because divergence E will be 0 in that location. Now we'll have to be careful with that in other circumstances, but if we consider waves in vacuum, divergence of E is going to be 0, and so I can rewrite the curl E as just the Laplacian of E. Okay, so that's what I'll do on the next page, minus the Laplacian of E. Okay, and so then this becomes, I have minus, minus del squared E equals minus epsilon naught mu naught d squared E dt squared. Okay, and so this is our wave equation in vacuum. It's usually written in the following way. I'll have just take this to the other side, and okay, and here's my wave equation. Okay, actually, let me write it one more time to make it look like what we do for waves on a string. So when we did waves on a string in 1B, we had an equation that didn't have a vector that we were operating on, but it had a look that was like this. Now we also didn't write it down with the Laplacian, but I'll simplify that in a second. Okay, so here's our wave equation in vacuum. It turns out this is the speed of the wave, is written right there. Now let me go and take a 1D example. So let's imagine that the electric fields only vary in one direction. Okay, and we're going to assume that what we're going to be considering is what we'll call plane waves when we're all done. Okay, but we'll consider that the wave varies only in one direction. It turns out that's going to be the direction in which it propagates. Okay. And we're going to turn this derivative, Laplacian square, we're just going to take one of the components. Okay, so let's take, for example, the z component. We'll assume that these are 0. If we do that, and we have what we will call the 1D wave equation, so you have d squared e dt squared minus 1 over epsilon naught mu naught d squared e dz squared equal to 0. Okay. And again, this we identify as the speed of the wave. In fact, it's the speed of the wave squared. Okay. And it turns out that that quantity is exactly the speed of light squared. Okay, so we find that we have a wave equation that, again, should look familiar. So this equation you've seen before. Again, we didn't have vectors in our quantities as we wrote down equations for waves on a string, but this is identical in mathematical form to the wave on a string. And so we're going to find that our waves that will propagate in the electric field, there's magnetic fields too here, and they'll propagate at the speed of light. And so the speed of light is the same as 1 over the square root of epsilon naught mu naught. And these constants came really just from considering electrostatic interactions and magnetic interactions independently. So we calculated the forces that magnetic fields exert on currents and the forces that charges exert on each other. We come up with these, excuse me, with these coefficients. And it turns out in combination, when you write down the wave equation, you find that that is in fact the speed of light. Okay. So this gives you something like 3 times 10 to the 8 meters per second. Okay, so it pops naturally out of these equations. All right, so now just to remind you, so this kind of equation, there's a general solution to it. It turns out if you pick any function, so take a function that is only a function of one argument, and that argument I'll call squiggle, like I did in 1B. Where squiggle is z plus or minus ct. Okay. If this is true, then it turns out, so if I look at this wave equation, and if I take, I'm going to take 2 time derivatives and 2 space derivatives of this function. It turns out because it depends only on this z and t in this combination, I can write that df dt is the same as df d squiggle times d squiggle dt. Okay, and so df dt is going to be equal to plus or minus c times df d squiggle. Okay. And all right, now if I consider the second time derivative, I'm going to end up with d squared f dt squared is equal to c squared d squared f d squiggle squared. Okay. Now I can go through the same exercise for the spatial derivative, and it turns out that df dz is the same as df d squiggle. There's only one argument that f depends on. It's that combination of z plus or minus ct. And then I do the chain rule, d squiggle dz. But because squiggle is just z plus or minus ct, this quantity just is 1. So it's the same as dfd squiggle. Okay, and the same for the second derivative. So if I take a second derivative, I just get that it's equal to the second derivative with respect to squiggle. Okay, so if I now plug that back into my equation, I have for the time derivative, so I'm considering this equation. It's taking this as a wave equation. F can be a vector, it's okay. So it could be the electric field as I've written it. C squared, oops, that's a minus. Okay, minus C squared, D squared F dz squared is equal to 0. So if I just plug in what I found from above, I'm going to have z squared d squared f d squiggle squared minus c squared d squared f, oops, d squiggle squared. Okay, just replacing these two with derivatives with respect to the only argument of the function, which is this c, I guess, not squiggle, but I like to call it squiggle. There you go. And so this solves the equation. Okay, so any function that is just a function of z plus or minus ct is a solution of this equation. Okay, and again, this is the same that we made the argument for in the case of waves on a string. And again, just to remind you what that means is basically a fixed pattern in space. So you have some, if I were to plot z here, and here's my function f of z, and so I have a fixed pattern in space like this. Let me do this, get rid of this. Okay, so this I'm going to say is some function f of z minus ct. Okay, so this is for t equal to 0. The pattern looks like this. The fact that the function only depends on z minus ct it essentially means the pattern will propagate unchanged along the z-axis. Okay, so if I look at t greater than 0, the point that used to be f equal to 0. So here is where f is equal to 0. So sorry, f of 0 in this case is here. Okay, so that point f of 0 will now move to where the argument is 0. So for t equal to 0, that's going to be at z equal to 0. For t greater than 0, if I want z minus ct to be equal to 0, you see that z is actually going to be positive. Okay, so the point where the argument of the function is 0 will move in z. Okay, so if I look later in time, this pattern, let's see if I can draw it identically again here. So the pattern will have moved like this. Okay, and here's the new location where that function used to be. So this just represents the pattern, some pattern just moving to the right in this case at the speed of light. Now if I chose that the function would be a function of z plus ct, I'm going to find that it moves to the left. Okay, the pattern, I can do the same argument and it shows it moves to the left. Okay. All right, perhaps that's enough for now. Let's stop there.